Good morning, guys. Today we're going to start Unit 3, which is our exponential and logarithmic functions. Today we're going to talk about exponential functions and their graphs. An exponential function has a base with an exponent. So in this example, the form is y equals x raised to the, y equals a raised to the x power. A is the base, x is the exponent. So that's the format for exponential functions. Exponential functions have a domain of all real numbers. They have a range that goes from 0 to infinity. Their y-intercept is 0, 1. And there is a horizontal asymptote at y equals 0. So standard exponential functions do not go below the x-axis. If a, the base, is greater than 1, the function is said to be increasing. If a is some number between 0 and 1, like a half or a third or 2/3, it's said to be decreasing. So I'll give you an example. An increasing function would look something like this. A decreasing function would look like this. It just goes the other direction. Noticing that they both go through the point of the y-intercept. They both go through 0, 1. So as a gets bigger, the graph gets steeper. So let's take a look at an example for that. I'll make me a table of values for 2 to the x power. 2 to the 0 power is 1, 2 to the 1 power is 2, 2 to the 2 power is 4. If I plot those points, there's 0, 1, 1, 2, and 2, 4. My graph will look like this. This is y equals 2 to the x. If I do the same for y equals 4 to the x, 4 to the 0 is 1, 4 to the 1 power is 4, 4 to the 2 power is 16. And I plot those points. There's 0, 1, 1, 4, 2, 16 is going to be way up here. So it gets steeper quicker. Okay. So as a gets bigger, your graph gets closer to the y-axis. All the transformation rules are the same. If you have a value that's added or subtracted to the exponential function, it moves it up or down. This one will go down 2. So let's take a look at that. If I graph 3 to the x power, I'm going to draw the parent function here, 3 to the x. I'll plot these points. Three to the x looks like this. And if I move that down 2, each one of these points comes down 2. So this one would be y equals 3 to the x minus 2. If the number is added or subtracted in the exponent, that moves it left or right. This one will move left 1. So I'm going to graph 3 to the x again. And I'm going to move each of those points to the left 1 because I have plus 1. Remember, if it's inside, it sort of acts like the opposite, you would think. So each one of these is going to move left 1. It'll look like that. The blue one is 3 to the x plus 1. Again, I'll draw my original 3 to the x. And I have a negative out in front of my base. The negative out front is going to reflect it over the x-axis. So if I reflect that over the x-axis, that means this point's going to flip over the x. A different color here. This point's going to be 3 below the x. And the 0.29 is going to be down here at 2 negative 9. And that's what the negative out front would do to it, flipping it over the x. If the negative is on the exponent, that reflects it over the y-axis. So let's reflect that over the y-axis. Draw my original. There is y equals 3 to the x. And if I flip it over the y-axis, that point's going to stay right there because it's on the y-axis. This one comes over 1 on the other side of the y-axis. This one moves over 2 on the other side. And it flips. So this is y equals 3 to the negative x. Exponential functions show up a lot with financial problems, dealing with money. This is what we call the general interest formula. It is a principal amount times 1 plus the rate divided by the number of times you compound it in a year. And all that is raised to an exponent, which is, again, the number of times you compound in 1 year times the time, which is, in this case, how many years you save the money or compound the interest. So, run through what the letters mean. A is the new amount, P is the starting amount, R is the interest rate, N is the number of times compounded in 1 year. You can compound it annually, and that's 1 time a year. That's N equals 1. Twice a year would be N equals 2. Quarterly, 4 times a year, is N equals 4. Monthly, there's 12 months in a year, so N would equal 12. You could also do it weekly. There's 52 weeks in a year, so that would be 52. And one that's not listed up here, you can do it daily. That would be N equals 365. If the interest is compounded continuously, we would use this formula. A equals the principal amount times E raised to the R times T power. E is a constant, very similar to something like pi. E has a specific amount. It's 2.718. It is on the calculator. And rate is whatever decimal form of percentage. If it's 6.5%, your rate would be 0.065. And T is the number of years. So let's look at an example. We have an investment of $5,000, and it's made on an account that pays 6% for 10 years. We want to find the amount if the interest is compounded annually. So annually means N equals 1. So let's look at what we got. My P would be 5,000. My rate in decimal form is 0.06. And T is 10 years. And we already know N equals 1. So if I plug that into my general interest formula, I want to use the big formula because I'm not compounding continuously. It's P times 1 plus the rate divided by N raised to the power of N times T. So again, this is my P, this is my R, this is N, this is N, this is T. You can put all that in the calculator at one time. Just put it in just like this. Make sure you use the parentheses. And we get an answer of 8,954.24. So example number 2 is we want to do it quarterly. Well, if we do it quarterly, that's going to be N equals 4. So that's the only thing that's going to change. Everything else is going to be the same. So 1 plus 0.06 divided by 4 raised to the power of 4 times 10. This should be a little bit more money than $89.54 when we did it for yearly. Not much more. It gives us $9,070.09. If we do it monthly, again, the only thing that's going to change is N. It's now going to be 12 instead of the 4. So if I plug those numbers in, should get a little more than 9,070. It's 9,096.98. And then if you look at example number 4, I see the word continuously. Anytime you see the word continuously, you're going to use the shorter formula. All right? 5,000, I hit the letter or the number E. E on a TI-84 calculator is above the divide sign. You would hit second divide, and it'll give you an E. And that should give you a little bit more money than the others. Be 9,110 and 59 cents. So that's how you use the formulas, mostly for investment purposes. If you want to figure out how much money you're going to need to save from the day you were born until you're 18 to have $100,000 for college, you could figure it out using these formulas. So that concludes day 1 of Unit 3. If you have any questions, remain on the Zoom meeting and we'll discuss them. Have a good day.